Okay, thank you all for coming. Our speaker today is John Ryan from Mbari, just down the road. By way of an introduction, John Ryan received a BS degree in biology from the University of Massachusetts in 1988. He worked in ocean science and terrestrial wildlife biology before pursuing graduate studies. John received the PhD degree in biological oceanography from the University of Rhode Island in 1998, and his graduate research focused on phytoplankton ecology in the northwestern Atlantic and was supported by fellowships from the Office of Naval Research and NASA. John began a postdoctoral fellowship at the Monterey Bay Aquarium Research Institute, Mbari, in the fall of 1998, working across biological and chemical oceanography research labs. He was awarded a NASA New Investigator grant during his postdoc, and appreciating the science and engineering collaborations at Mbari, John has since remained there and is now a senior research specialist. His research focus is on relationships between ecosystem processes and marine life forms, from plankton to whales. And I believe today he's going to talk about some of the data from a hydrophone in the middle of Monterey Bay. I know he just had a paper come out on that recently, and I'm sure there's lots more exciting projects on deck. So thanks for coming.
I think the volume can go on now. We were avoiding feedback. So yeah, many voices, many stories. We'll tell a couple of them, a few of them here. Thanks for being here sincerely, and thank you, Allison. Great to work with Allison. I've been learning from her. In fact, she really introduced me to the acoustics community when I started into this a number of years ago, 4 years ago. So let's start with the question that is mastered by the very young. Why listen? Why? So why listen? Well, we know Most of Earth's largest habitat is dark. Light reaches up to hundreds of meters below the surface, and sound can travel up to millions of meters. So sound is an amazing carrier of information in the sea, moving far and fast, more than 4 times faster in water than in air. So it's no surprise that marine mammals and other animals have evolved to use sound. For example, marine mammals use sound to communicate, forage, navigate, reproduce. So really essential to their lives. And that means just by listening or recording and analyzing, we can learn a lot about their lives. And it also means we have to be careful about the noise we put into the ocean because it can interfere with their lives. And in late 2016, NOAA released their Ocean Noise Strategy Roadmap. The idea was to integrate their efforts across the National Marine Sanctuaries and across NOAA to understand noise impacts toward improving mitigation of those impacts, which include what you would immediately expect: interference with communication, so the masking and impairment, behavioral disturbance, for example, causing them to leave a habitat that they need to, hey Nick, they need to live in. And we're focused on a project right now with NOAA and NPS with regard to one noise type and harbor porpoise. I'll get to that later. It can cause acute or chronic stress, and there have been measurements of stress hormone levels that have indeed indicated this. And then, of course, if the sound is extremely intense, it can cause physiological damage to tissues and behavioral responses that are even more life-threatening in the case of beaked whales that rocket to the surface from very deep in response to Navy sonar, for example. A severe case of decompression sickness. So how do we listen? We're really fortunate to have a cable, 52 kilometers long, that connects Moss Landing to the deep ocean, well, the continental slope just outside the bay. So that cable begins down at the end of the island, connects into Mbari, and there we are. Right there's my office. And then, cable stretches across the northern shelf, south of Santa Cruz, avoiding Soquel Canyon, and then runs down off the edge of the continental shelf break and slope down to a feature called Smooth Ridge. And in a moment, we'll switch over to video of the Mars node. There it is with the cable coming in from the right, and the science ports are on the leading face. You can see there are 8 of them. And it still amazes me, you can plug in the deep, high-pressure, corrosive environment, and it just works. An electrical device just works. But anyway, you back away, and you see we're in kind of a natural geological amphitheater. You back away far enough, and you've been staring at it too long, it might look like an ear. So anyway, it is a great location to listen. So one of the reasons it's a great location to listen, besides that natural open to the Pacific view, is we're in the middle of the sanctuary. So we get a chance to understand sound in one of the National Marine Sanctuaries, which is a priority for the sanctuary program. And of course, the sanctuary is in the middle of an extremely productive ecosystem, as we knew. The cooling of the waters from the North Pacific subtropical gyre toward the ocean margin we know how that's driven by the wind, and it's responsible not only for the invention of the wetsuit, but also extremely high levels of nutrient input, which fertilizes the entire ecosystem. And the whales and the other marine mammals really know this. We're a favored foraging habitat, as you'll see from some of the data later. And it's not just important foraging habitat, it's migratory habitat. So we really are just in a great place to listen to many species and learn from what we hear. This is a day in the life of the soundscape. On the x-axis, you're looking at 24 hours. Y-axis, frequency from 5 to 100,000 hertz. Range of human hearing is highlighted in green, about 20 to 20,000. And it's important for us to sample within and outside our range of hearing because there are some important things happening outside of that. But you get used to looking at these, and right away you can label, a good bit of blue whale activity. Fin whales throughout the day pretty much. There's a few earthquakes. And boats passing by, transits, some dolphins up there. So, this gives you a sense of not only the variety of information, but how dense it is, and kind of the challenge in distilling mountains of data into scientific understanding. So it's just a little hydrophone, a little tiny thing. You can hold it in your hand, but it produces 2 terabytes of data per month. So that is our challenge. And we use a number of methods, semi-automated analysis, like just producing these spectrograms. Then I can go in and manually examine them and label things and learn from that. But we're also really working hard on signal processing and machine learning methods that give us automated detection and classification of specific sound sources so that we can examine their variation through time. Our project goals are in both research and education, and I'll touch on both of them. In research, we want to understand the presence and activity of marine mammals and how that presence and activity relates to variations in the ecosystem. And lastly, how the nature and consequences of our noise can impact their lives. For education, we're aiming to enrich educational programs and media with these recordings and the scientific content we derive. Here's the project team at MBARI in the upper left block. You know, people in marine operations, engineering, education, and research, and internal collaborators, as well as a number of institutions we've worked with. As I mentioned, Allison was helpful not only in connecting us with people she's worked with at the Naval Postgraduate School, for example, but of course we continue to work with her. That Humpback whale paper she mentioned, she's a co-author on it. So great, really great this sanctuary is wonderful for many reasons, including its collaborative environment. So I'm going to start with Humpback Whale Song, which, if you've listened to the live stream recently, this is a good time of year for them. There's singing peaks in November through January, typically. So you should hear a lot of them. They sing more at night than during the day, so even better if you're a night owl. But, you know, this paper, it's really kind of a stunning result where they observed, they were listening both off Western and Eastern Australia, and they noticed 2 singers coming over from the Indian Ocean, joined 82 singers in the Pacific, and over a period of about 2 years, the song of the 2 replaced the song of the 82. So that right away tells you that there's this learning process going on, and there's sharing of information, and there is, as it's called, cultural transmission. And this more recent paper from this year shows how there may be places where along their migratory paths, different populations intersect and they can exchange that information, that culture. So that it's part of the engine driving the evolution of Humpback whale song. And here we are, you know, extremely productive habitat, and as I say, the whales know it. This is a description of biologically important areas, BIAs, from Kalambakitis et al., which, you know, may also be a convergence, right? Because foraging ecology is really rich here. And if you looked at Jared Santora's data on forage species for whales, Jared's up at UC Santa Cruz, you know, that data over many years shows how forage fish and krill are particularly rich, say between Monterey Bay and Bodega Bay, you know. And the highest concentrations of, in this case, humpback whales are off this central California region where the foraging is so rich. So let's look at different time scales. This is based on 3 years of continuous recordings, almost continuous, from the Mars Cable Observatory. And the shortest time scale we think about is day-night. And what you can see right away is they are singing more at night than during the day. Solar elevations below -12. It's pretty even across the night. Close to 70% of the time, we're hearing song. This is during the seasonal peak, by the way, November through January. And there's a reason for that. But then we move into dusk dawn, and it drops off to about 52% of the time. And we move into daylight, and not only does it drop off, but there's a linear decrease towards solar noon. So they're singing less with higher solar elevation. So the next time scale we would naturally think about is seasonal. And this is a seasonal climatology based on the 3 years of data. And right away in the upper left, song, you can see that annual winter peak, November through January. And about 76% of total song occurs during those 3 months. So 3/4 during 1/4. And then to the right of that, in orange, you see the song length. Individual songs from the start in the fall to the end of the peak in January, song lengths are increasing. Okay. And then lower left, we've got day length. And of course, that peak in song is associated with the trough in day length, which is an indicator of so many things about the ecosystem and about their migratory lives. But let's think about their migratory lives in the lower right. This is humpback whale sightings per half-day trip. Karen Forney of NOAA processed the data from Monterey Bay Whale Watch. Now, Whale Watch data is biased, but it's biased 320 days per year. So, if you're looking for low-frequency patterns, you're probably going to see them, especially with an abundant species like humpbacks. And what you can see is humpbacks are present in the summer, abundant in the summer, but they're not singing. So that right away points to how it's a behavioral control. And by the way, interrupt at any time with questions, please. And then the sighting levels stay high into November when song rises up to its peak. So they're both abundantly seen in the bay. By the way, Monterey Bay Whale Watch covers the southern bay, mostly. But then song is still high in December and January, but you see the sighting numbers dropping off in southern Monterey Bay. So that's an indication, of course, of these seasonal changes in not only leading to the rise of song behavior, but also the migration to low-latitude breeding grounds. Now, we don't know whether they move offshore, they move around the peninsula and use habitat there. We just don't have data to answer that. But what we may be hearing are the populations that are coming from further north and singing along the way, further offshore that we don't see them in the bay. So that's a rough seasonal story. How about interannual? This region is so strongly affected by interannual variability physically. And what we see is from the August of 2015 through July of 2018, the first full 3 years, we see the seasonal cycle every year. And yet it looks like between the first and the second year, total song increased. And it did by about 44%. And again, big increase between the second and third year. So there's a really strong trend here in this method of detecting behavior. And when we go to examine this, we want to take sort of an ecosystem level view. And we're doing that with a number of data sources. I mentioned the Whale Watch sighting data, really good to compare what we see with what we hear. Sea level, which tells us a lot about the underlying ecosystem, the depth of nutrient source waters, physical anomalies that can affect productivity and habitat. Forage species, absolutely, and of course forage species from Jared. And then at that magical step of translating inorganic matter into food, primary productivity, and that's happening. I wonder if I can point with this. Yes, good. These green diamonds are the stations where Francisco Chavez monitors primary productivity about every 3 weeks, so good sampling there. And off Santa Cruz Wharf is where a neurotoxic compound from microscopic algae, domoic acid, is measured by Rafe Kudella's lab. And we know that compound, it would cause amnesic shellfish poisoning in us, and it can affect the health and behavior of marine mammals, including whales. So we're trying to, and of course winds that drive the upwelling. So we want to take this ecosystem level view. So let's sort of step into that. Let's start with the simplest hypothesis. Song, on an annual basis, more than doubled over the 3 years. And first hypothesis is that there was more song because more whales, exactly. So surveys said, literally surveys said, there was an increase slightly between the second and the third year, but the first year actually had the highest sightings in the bay when we had the lowest amount of song recorded. So that doesn't immediately explain the 3-year trend. Okay, so now we're going to use modeling of sound transmission. And this is done by the Naval Postgraduate School, John Joseph and Tetiana Margolina. And what you're looking at is a map of received level, RL. Lower received, the star is the location of the hydrophone. And what this map says is, depending on where I place the whale in this map, my received level would be this. So you can see the warm colors around the hydrophone. That means if it's close to the hydrophone, we hear it well. As it's farther away, we don't hear it as well. And of course, whether or not we hear it depends on the background. So yeah, and this tells us a number of important things. And the first thing is, look at southern Monterey Bay. Received levels from there are pretty good. So comparing song recording at the hydrophone and sighting data from the southern bay, it's a good comparison. It's useful. And then, so we wanted to model this so that we knew if when the whales are using nearshore habitat, could we also hear them singing? Right? Because there are years when they're driven to use nearshore habitat for foraging, and if they're still there when they're singing, would we hear them? So the next simplest hypothesis comes from this model study. And really, I guess I didn't point to it, but Scott Benson and others published a study in 2002 that showed during a warm anomaly, in that case caused by El Nino, the humpback whales moved into the bay. They were using the habitat in the bay more. And our question is, if they were in the bay, onshore versus offshore, would we hear them differently? And so now we're going to quantify those received levels with 0 being the hydrophone and distance onshore and offshore, right and left respectively. And what you can see is the received levels fall off quite similarly, about 20 versus 21 decibels from 0 to 30 kilometers offshore, roughly. The point is it doesn't fall off much more steeply toward the shore. So that doesn't really suggest that if, when we had that warm anomaly in the first year, which I'm going to show in a moment, if they moved into the bay, this doesn't suggest that we would hear them less. So let's turn to that warm anomaly. What you're looking at in this top plot is from 1993 through 2018, quarterly mean sea level anomalies for the whole California current system. And what you can see, that gray bar labeled Y1 is the first year of our recordings, year 2, year 3. And you can see we deployed our hydrophone in the highest sea level anomalies in the California current system in the last 25 years. So really anomalous, physically anomalous. And then over the second and third years of recording, well, first it dropped off steeply, still remained positive, the anomalies, but then kind of leveled off to a more moderate high sea level. And of course, that high sea level was caused by warm conditions. In 2015, the warm anomalies were pretty much throughout the region. This was the so-called warm blob, which we're apparently starting another one now. Then year 2 and year 3, you can see there are still warm anomalies, but there are also moderately cool ones or near neutral. But what I want to draw your attention to, and I don't know if there is oh, you know what? I've got something better than a laser pointer. It's a new technology. And, this near-shore habitat, which is primary foraging habitat for the whales, right? In that first year, the warm anomalies intensified toward the coast and toward the surface, really heavily impacting their foraging habitat. Even though a warm anomaly persisted below the surface in the next 2 years, it was much closer to neutral, even slightly cool during the next 2 years in their foraging habitat. So in terms of the perspective of a whale, that's a significant rebound. So now the next hypothesis is, well, what if, with that warm anomaly, what if it changed how sound propagates between the whales and our hydrophone? And that could happen if the picnic line became anomalously strong or deep, for example. If it was anomalously strong, then whales singing above it would have their sound more attenuated. Or if it was exceptionally deep, the whales might more frequently be above it to have their song attenuated. But we analyzed density profiles from this station and this station, and basically the warm anomaly was pronounced strongly, but the density gradients in the upper water column were at about the same depth and the same magnitude across all 3 years. So that really is not, that doesn't seem to explain, or it doesn't offer a possible explanation for that interannual trend. So we're exhausting hypotheses here. What about the ecosystem influences? So let's go back to our trend. This is Humpback song more than doubling in the 3-year period. Let's go to the primary driver of the ecosystem, the winds. The upwelling and cumulative upwelling follows a similar pattern, increasing greatly over those 3 years. Correspondingly, primary productivity increased significantly during that time period, leading up to forage species that whales care about even more. Krill, negative anomaly in the first year, strong positive anomaly by the 3rd year with a neutral in between. So these are all conditions that could promote health, successful foraging. And from an energetic standpoint, we might interpret that increased food resources would provide more energy and perhaps even time for song behavior that rises in importance as they move into winter. And then lastly, not all primary productivity is created equal. Some of it is toxic and poisonous. And that first year, when we had the least amount of song, the most sightings, was the most toxic year. And McCabe et al. Studied this toxic bloom along its whole extent from roughly Monterey Bay up to Washington. And what they found is that marine mammals, including whales, were poisoned all along here. The nearest ones in which domoic acid was detected were off San Francisco Bay here. So there was this potential for a neurotoxic compound to influence behavior, And there's more to the story. This is the paper. There's Allison. Okay, that whole paper was just about one question, really. When? When does humpback whale song occur? Now we want to know, there's so much more to humpback whale song. You've already heard this. Let's hear it one more time. And it's probably best, I'm going to turn this down a little. So that's a phrase, right? The humpback song is organized with song units, the shortest individual sound you can discern, which are organized together in a phrase. In this case, this is a phrase and a half. These two plus these four is one phrase. I just like the symmetry. Now, phrases are repeated as themes, and a collection of themes is a song. And they can sing for on the order of a day, stopping to breathe. The song sessions can be extremely long. So it's hard for us to listen on whale time, right? They're singing on their time scale, which is big. And it's hard for us to hear the structure and how it evolves in a song. So what we'll do is we'll put this phrase in the context of the whole song and play it back at 8x speed. And that phrase, by the way, is sort of toward the end, one of these. Yeah, and their songs, we've recorded songs up to like more than 30 minutes. And they remember them. That's the amazing part. So yeah, and okay, I can sit here and I can label these song units. I can put whatever label I want, describe their sequence and how it changes through time. But what we've, currently there's no standard lexicon. You can go to 2 different studies and they label the same type of song unit differently, And so what we're looking, yes, Nick?
Are you saying that you could get that same 7-minute pattern again?
Absolutely. In fact, I'll show you a little later 2 songs, one after the other, and it's like exactly the same. I see that again and again. But they also improvise a lot. Okay, I'm anthropomorphizing. But yes, they'll seemingly repeat a song maybe exactly, then they'll shorten it or lengthen it and change it up. Anyway, I interpret that they are exploring. So what we're trying a method of unsupervised learning, machine learning called topic modeling. And one of our engineers who works on autonomous vehicles was using it to discover the state of the vehicle. Was the vehicle in trouble in any way? And he said, hey, I think that might work for your Humpback Whale song. So this is work that Danelle Klein, she's the lead engineer on the project, and Ben have really led. And our summer intern, Tom. So here you see the song units, right? Individual song units. There's one, another of that type, and these 3 in between. And look what the topic modeling with no training whatsoever is doing. It's assigning topics. It assigns orange to this, and when it sees it again, it assigns orange. Okay, I'm, a topic distribution that's dominated by this topic colored in orange. And then these 3 in between, are distinguished as well from the background. And as this song evolves, you get frequencies dropping, new topics arise. So it's early, but it's one approach that we think could be really helpful to more objectively define this lexicon and to study song structure and its evolution. So that's work in progress. Now, the second of 2 species I'd like to focus on is the blue whale. You've already heard the D call. That was that down sweep, that first one we heard. Here's a B call. Oh, the D call is made by both males and females. The A and the B are made only by males in something referred to as song. Back on full. Down. So a B call comes in 2 parts, long, low tonals. You'll hear a pause between them. And maybe some ship noise too. Oh. We'll look at how that fits into a song on their time scale. And I'll turn this one down a bit. Oh, this is the one with ship noise in the background. So yeah, the A call is this pulse train. So if we were to look, we'll zoom in a minute, but here is a 24-hour period. Again, 5 hertz to 100 kilohertz. Way down low are the blues and fins. And what you can see is, look at, these are the A calls. That's a pulse train right there. And see how it has its own cadence? These are the C calls with their own cadence. And these are the B calls. The fundamental, second and third harmonics. We usually study the third harmonic because it's most distinct. But for example, you know how it was in 2 parts? There's a double one right there. And let's take a closer look. Here's that pulse train, and you can see its pulse nature, the A call. Here's the B call, a single tonal in this case. And the C call down at 10 hertz. This subwoofer can't even do that. And then here's that D call, the down sweep. And this is really, I tell Will Astrike that I wish I had his thesis. He has the best thesis. He's using the so far 4 years of recordings from Mars to study all of these blue whale call types. And in Jeremy Goldbogen's lab, he is deploying tags on the animals that give you a lot more information, so behavioral context. So let's just look at one example of how he's integrating 4 years of recordings with what he's learning from tagging the whales. So what this is it's a call index for that blue whale B call, the long tonals. And they're pretty much not singing during this period. And then you can see their song rise up during this period to a peak in November, just like humpbacks. Fins also peak in November. But look at how, as it rises up, it diverges with night and dusk dawn rising above day. And then as we get into October, November, daytime calling approaches more closely to the nighttime calling. So there's this seasonal modulation of dial behavior. They're getting closer to even as you go into the season. So here's Will's hypothesis. He thinks, well, closer to summer, they're more focused on foraging. And if when they're foraging, they're not singing as much, then, and they're foraging more during the day, maybe that's why this kind of falls below the nighttime calling rate. And so here's data from one of the tags he put on a whale. So, yeah. Oh, yeah.
What's the index?
So it is, it's the equivalent of Anna Sirovic's fin whale call index, basically, where here's the issue. If you have calls that are always separate and distinct, then you can use a method to detect and classify individual calls because they will stand out in a spectrogram if there's no noise washing over them. But if you have whales calling over each other, it becomes a continuous noise band, and you can't detect and classify individual calls. So what we do is pick the frequency where most of the sound energy is, pick a background where there's not a lot of noise, and do a difference or a ratio. How much does that peak rise above the background? Yeah, and it's kind of very integrative on this time scale, right? Because, yeah, there's more to it that I can talk about later. Okay, so now here's the view from the whale. It was swimming along one day and somebody stuck a suction cup on its back. It may have noticed. And then it had these three phases where it's hanging around at this latitude, right? Pretty much not moving. And you can see it's calling. Well, number one, here's the daytime calls, nighttime calls. You can see during this period, it was calling a lot more during the night than during the day. And this was a time period when the tag data also shows it doing a lot of lunge feeding during the day. So right away you've got this, not calling as much during the day, but feeding a lot. Then it went into this 4-day period where it was not calling much at all, day or night. And the tag data says that the animals were racing. Like blue whale males will apparently race, like jet around. And that's John Kalambakidas who's observed that. Then it goes into this mode where, look, day and night becomes much more even. So the total calling is kind of a similar magnitude when they are calling, but there's this big shift from dial variation to more even. And this evening happens as the animal's migrating south. So that's kind of how he's using tag data to get insight on behavior that may explain what we're hearing at our hydrophone over long time scales. We are getting a chance, we study animals that are here all the time, making a lot of noise, a lot of sound. And that's important. We're working on other species, but just as important are the species you might hear seldom, but if you hear them at all, it's significant. So cryptic species like the pygmy sperm whales, we're working with Carly Merkins at NOAA to, and we may even turn up the sample rate of our hydrophone for her. It's already 256 kilohertz. We might go up to 512. Why? Because she wants to be able to capture the top end of those very high frequency clicks that they make. And she's already identified their clicks in our time series. And for a species that you don't really know its distribution, that's helpful to understand. And then North Pacific right whale, on the order of 30 animals left. And we're working with Catherine Burchak on this to evaluate whether we hear them, whether using this habitat, because they have been observed, obviously north, we're off Alaska, but also south of us. So they want to know if this is important habitat for them as well. Both of those are kind of early. So now turning to the second type of sounds, we either hear biophony, sounds of life, anthrophony, our noise, geophony, the earth. So here's an example of anthrophony, and I'm going to turn up the, turn this down, turn this up, and listen, you'll hear these dolphin whistles as well as these sounds from us. Yeah, so those are seal bombs, explosives used in fishing operations for one of two purposes. One is to get animals out of your net, mammals that come in because it is a bowl of food. You're pulling in a net, which is their dream. and they're very good at getting in there and chowing down. And I was talking with one of the fishermen the other day. He said he's even seen pelicans get in there and, pass out from food coma, just right in the net, So yeah, it's a good place to be. And so they either try to keep them out by scaring them away or get them out. And there's concern, though, of course, that it's a dinner bell effect. But anyway, the second use is to steer fish into nets. That happens as well. But, no doubt we need, fishermen need to be able to keep these mammals out of their nets for the safety of the animals and the safety of the fishermen. And if anybody's going to be able to figure out a better way than these explosives, it'd be fishermen. And that's what I was talking with them about. So yeah, that's we didn't even know these were happening much in the sanctuary till we started listening. And here is a study summary from August of 2015 through February of this year of the number of detections of explosions per hour for every hour of every day. And right away, you see the seasonal pattern. And when you sum it across hour, you see during the nighttime, that's when most of it's happening. It's consistent with the squid fishery. And, we had as many as 1,200 or so in a single month, whereas off Southern California, as many as 38,000 at one site in a month. So it's a much bigger problem there. As many as 88 in an hour compared to 500 in an hour off Southern Cal. So yeah. And we're working with NOAA on this problem. How can we inform management? So last bit I want to touch on is, access. We want people to be able to access the data, the recordings that for research and educational purposes. And we have a listening room online, which includes live stream, just a web player. We just added an Alexa skill, so you can tell your smart speaker. You say, Alexa, ask Ocean Soundscape to play the live stream, and hopefully it'll work. It has been working. So we also have, if the live stream is boring, which it's not this time of year, it's really exciting this time of year, but if it is boring, you can tune into the recording library, pick different sound sources and listen. You need a subwoofer for some of them. Welcome to borrow this one. We've been working on exhibits. We just opened an exhibit at the Sanctuary Exploration Center in Santa Cruz, right across from the wharf. And basically, it's you walk up to a perspective view of the bay, and these buttons have concentric rings with different thickness and spacing, which gives you a hint about frequency. But it's like the videos you've been seeing. You first engage with the sound, as a spectrogram and as a sound. And then you wonder, what is that? And you get the reveal of the sound source. And Lisa Utall at NOAA led our efforts together with the Exploration Center. David French at Mbari, he's really the mastermind. He's the one, when we started this project, he said, you know, John, I think I can make you a mobile exhibit for about $300. And he did so with his personal subwoofer, scavenged some of the scavenged electronics, and some minor electronics that he bought, and a Pelican case. And we started bringing that around. It was like right away we noticed, okay, this is a good way for people to connect with ocean life. Because otherwise, you know, we can stick our head underwater, but there's a lot more than we can hear with our ears and in the near shore zone, which has other masking. So that's open. We are working with the aquarium on their deep exhibit to provide a soundscape. We've gotten into documentaries. Our summer intern, Daniel De Leon, he came and did machine learning work with us. Then he goes to a conference because the NSF REU program sends their students to a conference. And someone from Google at the conference sees that he's using their technology, TensorFlow, and so they decided to do a story on him. And it's something like 8 million views. He said this has been good for his job applications. And then we participated in a documentary by BBC last summer. It was released in the UK this year. It'll be released early next year here on PBS. We participated in a water-themed concert at Monterey Symphony. Incredibly beautiful music. And they really just kind of wanted a bit of a scientific perspective on sound in the sea. And we did play some of our sounds through amazing subwoofers beneath the stage. And then the BBC producer brought our sounds to this music festival, and Joshua Miller, also known as the Musical Yogi, got them into Burning Man. And he's now touring with the sounds of the ocean. He's going on a tour, and he plays acoustic percussion instruments beautifully. And so he's got this ocean soundscape background, and he's playing on top of that, and it's really engaging. Relaxing, too. Yolandi Harris at UCSC, she was the first one to take our recordings and do a sound walk, an immersive sound walk. That also allows you to hear the ambient soundscape, but it takes you on a bit of a journey as you walk along the shore. And then there's Josh's Sounds of the Ocean. That hand pan is super beautiful. And then this is the last thing, last note, right? So we deployed a hydrophone at the end of July 2015. We swapped it out in the middle of 2017 with the exact same thing, basically. And then Naval Postgraduate School, this is Kevin Smith, John Joseph, and Paul Leary. It's a directional hydrophone. So right now, our original hydrophone is omnidirectional. We have no idea where that sound came from. But now, at least below 4 kilohertz, we will know the direction of the sound source. They've already driven donuts around the Mars Observatory to convince themselves that it's working. And the other day, I sent them some blue whale calls. They sent them back to me with direction. And I plotted the vector on the map. It pointed right to Carmel Bay. And then our student, Will Astrike, talked to the whale watching boats, and that's where they're seeing blue whales. So the idea is that we can, ideally, let's say someone wants to go out and put one of those suction cup tags on a blue whale. We can tune in, find out what direction to go from the hydrophone, and more efficiently go find the whales we're studying, for example. So yeah, that's a cross-section of some of the work going on with the Soundscape project, and as it looks like maybe 10 minutes, so glad to answer questions.
So do you have a theory about the sounds and what it means? Like, a dog barks when it's happy, or, cat meows. Are you starting to find trends?
Yeah, I think there are like a few steps we can take. The first step that's pretty straightforward is, what's the pattern of the sounds that they make? What is the pattern? Getting from pattern to meaning is difficult. And I have this idea that I'm really passionate about. and I was telling my friend about it, I say, you know, okay, sound carries information in some way maybe from the start to the end of some sequence of sounds, there's an accumulation in their neural network that leads to information and its interpretation. And I'm going on about how it's got to be accumulation. And my friend says, John, maybe you just have to be a whale. You know, so, you know, I'd like to think that from the perspective of a human who did not evolve in the ocean, much for millions of years longer than humans, and a medium in which sound travels so well, and they obviously use it for everything, how did their neural net evolve to use sound? Maybe I can't even imagine that, you know, because my brain works in air and in some ways, I think, simpler ways with sound. So yeah, is that kind of getting near your question?
I guess you'd have to, you heard a noise and then you saw them feeding, and you hear that over and over again, you go, okay, well, that's the noise they're feeding. And
Yeah, thanks for clarifying that.
You know, I guess if you'd have to have 2 or 3 people, you'd have the noise, and then you'd have to have somebody watching, and be very.
Thank you for bringing that up because, you know, when I mentioned patterns, one of the patterns is, okay, these are the patterns on the hydrophone. What are the patterns on the tags? And here's an example. Those decalls from the blue whales, the down sweeps, they make those after they've been down deep, maybe 100 to 200 meters, lunge feeding on krill. And they'll come up to about 30 meters and they'll make that sound. Okay, so it's apparently associated with feeding. Now, what does it mean? Does it mean yum? Does it mean this aids the digestion? Does it mean, hey, everybody, this is a good spot? And some of the work Jeremy Goldbogen's lab is doing on so-called supergroups, where you have an unusually high number of animals packed into one area foraging, there's some indications that the call rate is elevated during those times. Okay, now we get into, you got to normalize it to the number of animals, but there's a possibility that this could be cooperative behavior for when they find good foraging spots. And someone, Dave Cade, working with Jeremy Goldbogen, is working on a paper on that right now.
John, back on that song, because I liked it a lot. It probably was your greatest hits pick, but the x-axis went 8 minutes. That's real time. That's nature time.
Yeah, so.
I heard it in 1 minute, something like that. So how long is a whale song?
Yeah, so both of those axes lied to us. 8 minutes didn't go by that fast, and the frequency we heard was not the frequency they put out, because it pitched up when we sped it up. So that's one thing I wanted to clarify. Thanks for pointing to that. But now your question about how long are their songs? Well, I've heard them as short as less than a minute to as long as 32 minutes. And that one plot of song length as a sort of the distribution, the non-parametric box plot of, okay, when they first start in the fall, the median song length is around 5 minutes. By January, it's 10. But it's not just the median that's increasing. The quartiles are all coming up, too. So it's like there is this overall shift in the song length. And you know, how that song length depends on age of the animal as well. It's a good question. How long they can hold their breath. And that may vary with age, I don't know. There's still a lot of questions about song length.
Most of the noises that you pick up, or are there like unknown sounds?
I have a mystery sounds folder. But the mystery sounds may not be mysteries to people who know more. Some of them are really strange, though, and fun. But yeah, I mean, after staring at a lot of spectrograms, you begin to see how often something strange shows up. That orca clip, that only is here because I was studying humpback whale song, and I said, that's in the same frequency range, but it doesn't look the same. What is that? So.
I know fish also make grunts and kind of vocalizations. Can you hear that sort of thing? Can you hear invertebrates scuffling around? But sort of like, what's the detection ability, how loud does a sound need to be for the hydrophone to hear it?
Yeah, there's a couple of good questions in that. And the first one maybe would be fish. Let's start with fish, because that's what you started with. Let's just say you had those spectrograms for every day of the year, and it's resolved every 5 seconds. Then you just take a month of data and you overlap time. And you look at an average day in the life of the soundscape. You see these clouds emerge, diurnal clouds, in a range that could be fish. I haven't studied that yet, but that's on the radar, like, oh, that's an interesting signal we can get when we examine the data statistically. Then the other thing is like crustaceans, right? When we first started learning about these seal bomb explosions, you know, they're sudden impulsive sounds, broadband, and people said, well, how do you know it's not snapping shrimp, for example? You know, right? And, you know, this, of course, depends on where you're recording. We're recording at 900 meters, and there are no snapping shrimp there. But also, even if you looked at the acoustic features of a snapping shrimp individual snap, extremely different. So we are always discovering more and more about what is in the soundscape. But for starters, we're picking subjects that we can kind of carry end to end, and not just for the science, but for the methods. And that's been really great. You know Danelle, and she's really doing an amazing job at helping us create engines that can not only take 4 years of data and analyze it in 3 days, but turn those models, those machine learning models, to real time, so we know what's happening in real time. So.
When you're trying to figure out what sounds you're hearing in these soundscapes, do you have to have, you know, like a live recording, like, okay, blue whale, you know, and you have to see the animal and have a hydrophone near that animal, or are you using other people's data and what they've recorded and associated with a certain animal before? All of that?
Yeah, I mean, I think we're leaning heavily on the past. You know, people have established these relationships by doing exactly what you describe, listening and seeing. And we're beginning to do more of that only in specific contexts, like all these different blue whale call types. How are they using them differently? And gee, how do their seasonal cycles vary? Because blue whale song has a peak in the fall, but blue whale decalls associated with feeding peak in the summer. And I mean, it makes sense, but no one had seen that before because they just didn't have the data. No one had seen it here. So yeah, it's, but you know, you raised something that's kind of interesting though. I went to my first Acoustical Society of America meeting last year, because mostly I've studied small things, phytoplankton, which are awesome. But here I am talking about things, and I'm describing the ecosystem. And somebody raises their hand, they say, it's a breeding behavior. Why are you looking at the ecosystem? You know? And I thought, well, you know, the opportunity here, especially in a place like this that is so well monitored, is to make those connections, because the animals are not separate from their ecosystem. They're responding to it.
I just had a question about, you know, the amount of data that you're collecting, and you're turning up the sampling rate. Now you're getting directional data. Are you limited at all by how much data you can transfer and process? It's the Mars Observatory, just like transfer as much as you want.
Yeah, the observatory, we're not running out of bandwidth there. We're not running out of storage, although we're getting raised eyebrows about storage. And NPS, right, as you can imagine, it's the Navy. They keep their own data. They keep the raw data, and they give us products. Right? So we don't have to store that, not much anyway. And, well, it's now time, after 4+ years, to think about migrating some of the older data onto tape and only keeping part of the raw data spinning on disk for analyses. So yeah, no, we're kind of figuring that out.
Are you able to associate like specific whales with the noise that you hear? Like if you and I sing the same song, we're going to sound totally different. So.
And you're going to sound better.
You can like keep track, like, oh, Jerry's coming this time of year again.
So are you thinking about the ability to identify individuals, or maybe even attributes of those individuals? That's a youngin', that's grandpa, you know. Well, I think it is possible, yes, and it would be the type of data you describe, where you're out there, you're seeing the animal, you've got the fluke ID, you're on Happy Whale, and you know who that is, and then you put your hydrophone in, and it's the only whale making sound around, and now you've got a vocal print, close to the animal, hasn't been distorted much by transit to a hydrophone. Then you can start to get these not just fluke prints, but vocal prints. I think it's possible. I don't know of anybody who's done that, but I can see it becoming a useful way to characterize the populations that come and go, and it's on the to-do list, I think.
I'm just curious for the processing of the data. You mentioned the pycnocline and how this, sounds can bounce if that pycnocline kind of shifts. How do you account for changes to like the speed of sound in the water for different things, for different times of the year? Is that just part of processing, or like?
Well, when we process the hydrophone data, it is received signal, period. We're not making any, especially since it's omnidirectional and we don't know how far away or in what direction that sound source is. We can't really go into that and say, oh, how would the density profile, really the density section between that sound source and my hydrophone, how would it affect reception or received levels? We just can't go there because we don't have the data. That being said, there are ideas that now we have two hydrophones, and if we know exactly what time it is on both of them, and we can get phase difference in arrival and spatial offsets, that there can be some kind of inverse modeling that I know nothing about that might give you an estimate of range in addition to direction. So yeah.
So, Coach John, do you have more questions? And thanks again for coming.
Sure.